I didn't say anything mathematical yet, but we are two speakers, Daniel and myself, and we met during Kedlaya's course on p-adic Frobenius structure. So today I'm going to introduce the p-adic Frobenius structure and tell you about some of Daniel's results, because at that point he was just starting his graduate studies, but now during his PhD, he proved a nice theorem, which I'm going to mention today. All differential equations will be ordinary, linear, and we will only introduce p-adic methods to study them, and I will try to explain what this is for and why this is natural. First part, I will mention what is equivalence of differential systems. So we have two matrices, A and B, whose entries are rational functions, n by n matrices, and let K be a differential field containing rational functions. Differential field, meaning that the derivation extends to K. So we have the operation d over dt on K. And we consider two systems. The u over dt is AU, and the v over dt is BV, where u and v are vectors of size n. Definition: system 2 is equivalent to system 1 over K if there exists an invertible matrix of size n with entries in K such that it satisfies the following differential equation. H over dt is AH minus HB. So this equivalence is a symmetric relation, because when you take H inverse, it will satisfy the same differential equation with the roles of A and B changed. But let's explain the algebra of this. What is the meaning of this differential equation? So let's call it star. And the meaning of star is this. First of all, if V is a solution to the system 2, then H times V is a solution to system 1. Assuming that you can multiply, that that this K contains the entries of U and V, say. So I'm just going to formally check this property. When we differentiate HV, we get, so we first differentiate H, and this is AH minus HB B minus H times the derivative of V, which is BV. These two cancel. We get AHV. So this, if we denote this by U, then this is AU. So let me write it that we do it formally. It may not work in general. I mean, multiplication may not work. It's not always possible to multiply H and V. Again, formally, suppose that U and V are fundamental matrices of solutions. So now they are of size n by n. Yes, it can be that the field, in general, you cannot multiply the entries of V with the entries of H. Probably we can make the field very big and that will work, but we will see examples when this is not obvious. I just want to keep it like that. I want to be able to choose any field K I like. If U and V are fundamental solution matrices, then let's differentiate this U inverse HV, again formally, assuming that we can multiply. So differentiate U inverse, it's minus U inverse A. This is the derivative of U inverse times HV. Plus, now we differentiate H. And now we differentiate V. And here, these two cancel, so we get 0. So this is a matrix of constants. If we can define it, then this is constant matrix. For solutions to star, are of the form with constant matrix sum. So these two properties tell a lot about the nature of this differential equation here. And let's give one example from Fuchsian theory of regular singularities, local study of differential equation on the Riemann sphere. So we take a matrix of size n with rational entries, with which is analytic at t equals 0. No pole at t equals 0. So let O be the ring of germs of holomorphic functions at 0. Near equals 0, and K be the field of germs of meromorphic functions. So we just add 1 over T. Then there exists matrix gamma, constant matrix gamma, such that the differential system du over dt equals to a of t over tu is equivalent to differential system with the constant matrix gamma. Maybe continue there. So systems of this form, if a system is in this form, one says that it has a regular, it's regular or has at most a regular singularity at 0. And there is a theorem saying that the three conditions are equivalent. First, that all solutions have moderate growth at t equals 0. Secondly, our system is equivalent over k to a system of this form. And thirdly, what is written here, that it's equivalent over k to a system of this form with a constant matrix gamma. This constant matrix gamma is not unique, but we can consider the monodromy around t equals 0. And this is what defines like the conjugacy class of the monodromy matrix, defines the equivalence class of a regular differential system. So we note that V equal t to the power gamma is a solution to this system, and the monodromy matrix is given by, so this t to the power gamma is exp gamma times log t, and when we go around 0 counterclockwise, log adds 2 pi I. So the monodromy matrix is exp of 2 pi I gamma. Then for two equivalent systems, monodromy matrices are conjugate because meromorphic functions have no monodromy around 0. And one can say that two regular systems are equivalent over k if their local monodromies are conjugate. Yes. The system, as I said, the three conditions are equivalent and they define a regular system. It's an equivalence class. Yes. M0 is the monodromy of this system around t equals 0. T to the power gamma is the matrix solution, is the fundamental solution matrix. And when we go around 0, it multiplies by this matrix M0. This is the local monodromy transformation. Okay. So let's just keep this example in mind. It's not directly related to the second part of my talk, which is about p-adic analytic elements. So I'm going to introduce the field of p-adic analytic elements. You mean this definition of equivalence? Yes. Yes. It's not unique. Okay, so gamma, this is unique up to conjugation. It's not unique. Yes. So if we look at eigenvalues, they are called local exponents. But as we know, local exponents depend, if we can transform the system and they will change by adding multiples of 2 pi I z. But eigenvalues of this matrix will not change. This is an invariant of equivalence over this field of meromorphic functions. Okay, so let's talk about something completely different for the moment. I will come back to equivalence. This field of p-adic analytic elements, by definition, will be denoted by EP, and this will be the p-adic completion of the field of rational functions with rational coefficients in the most naive and intuitive sense. So the elements of this field will be uniform limits of rational functions, such that when you pick some power of p and go sufficiently far in this sequence of rational functions, every two will differ, will be zero modulo this power of p. But now I'm going to work this out a bit so that we have a norm, and this will be a field. We will see that it's a field and it's a differential field. Yes, I'm going to specify it. So it's a very vague definition. It's a vague definition, not a definition yet. So we'll consider, so let's Gauss norm on polynomials with rational coefficients. Polynomial will have the norm, which is the maximum of p-adic norms of its coefficients. And the p-adic norm of one rational number is p to the minus power of p, which divides this rational number. In fact, one can take any number between 0 and 1 and raise it to the power of p, which divides this rational number. So this norm a p is p minus p-adic order of a. Two rational numbers, like a rational number will have a small norm if it's divisible by a high power of p. Oh, yes. If this number is big, it means big power of p divides a. And now this is a non-Archimedean norm, meaning non-Archimedean norm, meaning that it satisfies two properties. When we sum two polynomials, the norm is less or equal. Okay, let me shorten Gauss to G, because I will have to write it many times. And secondly, the product, the Gauss norm of a product is the product of Gauss norms. This is called Gauss lemma, and this is why this is called the Gauss norm. okay, it has it uniquely extends to the field of fractions of this, which is the field of rational functions. And still satisfies the two properties, 1 and 2. So the norm of a ratio is just the ratio of Gauss norm. I mean, f and g are two polynomials here. With this norm, u of t is an incomplete discretely valued field and then EP is, now it's the definition, is the completion. Of this. It will also have the Gauss norm by construction. Let's give an example of an element of EP. Take an infinite power series such that with an in QP and the norm of an tends to 0 as n goes to infinity. Then modulo every power of p, this is a polynomial because it will drop modulo at some point. Therefore, it's a limit of rational functions in this Gauss norm. Limit of polynomials. It's a very simple example. We will see more sophisticated examples later in this lecture. Now we have continuous operations, which I will define on Q of t, but they will extend to EP because they are continuous. The first operation is raising p to the power p. Then the Gauss norm of this is obviously the same as the Gauss norm of f of t. The operation is continuous, preserves the norm. And secondly, the derivative. It's again continuous. Let's check it on polynomials first. On polynomials, the derivative of a polynomial looks like this. It's clear that the Gauss norm is less than the Gauss norm of ai t to the I, because the p-adic valuation, p-adic norm of I times ai is the p-adic norm of I times the p-adic norm of ai, and the p-adic norm of I is less or equal 1. I is an integer. Integers have the p-adic norm less or equal 1 because they are divisible by positive powers of p. And now on rational functions, if f and g are polynomials, then we take the derivative of the ratio. It's f prime g minus g prime f divided by g squared. Now I use multiplicativity of the Gauss norm, so it's norm of g squared here. And I use the first property, that non-Archimedean triangle inequality. So it's less or equal than the maximum of Gauss norm of f prime times Gauss norm of G, Gauss norm of F times Gauss norm of G prime. And now each of these, the Gauss norm of F prime is less or equal than the Gauss norm of F. Gauss norm of G prime is less or equal than the Gauss norm of G. So they are both less or equal than Gauss norm of G times Gauss norm of F, Gauss norm of G squared. It's less or equal than the Gauss norm of Fg. Therefore, these operations, derivation and substitution of t to the p, are also defined on EP, the field of p-adic analytic elements. Okay, and now we will combine the two things we were talking about. Notion of equivalence with having K as the field of p-adic analytic elements. But for that, we will have to restrict to matrices with coefficients in Q. P-adic Frobenius structure. We take A to be a matrix with rational entries and observe that if U is the solution to this linear system, then V of t is U of t to the p to the h. I take h an integer bigger or equal 1. Solves the following system. P to the h times t p to the h minus 1, a of t p to the h v. Definition. A p-adic Frobenius structure of period h for the differential system du over dt equals au, or for the matrix A, which defines this system. Let me write it in full, because U is not a solution. It's just the notion for the differential system. Is a matrix I in GLN EP satisfying this differential equation d phi over dt is a of t phi minus p to the h, t, e to the h minus 1, I of t, a, t to the power p to the h. So a p-adic Frobenius structure is an equivalence between the original differential system and the pullback under substitution t to the power p to the h. If h is 1, we just say it's a p-adic Frobenius structure, or when h is clear. So, notation, when h is 1, we call it a p-adic Frobenius structure, without mentioning the period of this Frobenius structure. So, why would one look at such a thing? It's very rare that a differential system has this property for infinitely many primes, for all but finitely many primes. In fact, differential systems coming from algebraic geometry have this property for almost all primes. And we will see examples when a system has such a Frobenius structure for almost all primes later today. And in general, it is expected that this property for almost all primes is equivalent to being coming from geometry. It's very hard to spot such systems if they don't come from geometry. Probably no example is known. Then this notion goes back to Bernard Dwork, to his deformation theory of local zeta functions of algebraic varieties. At the beginning of his lecture, Duke van Straten was mentioning precisely Dwork's example. So he took the Legendre family of elliptic curves, and it turns out that when we solve the Picard-Fuchs equation for this family, the differential equation satisfied by period integrals. Then a holomorphic solution at one singularity, which was t equals 0 in that case, if we truncate it, this polynomial knows about which curves in the family are ordinary and which are supersingular. It knows about how many points over fp each curve has, but only modulo p, the truncation. What Dwork discovered was that when we don't truncate, so take the whole solution to this differential equation, take the period integral, which is a hypergeometric function, then we can compute the number of points over fp on each curve in the family exactly. And the way we compute it uses p-adic properties of the hypergeometric function. We will come to that in examples already in the first problem session, but I'm going to explain it further. Now I just want to say that this notion comes from deformation theory of local zeta functions, and such matrices, phi of t, like matrices depending on t, when they are attached to families of algebraic varieties which depend on the parameter t, then their characteristic polynomials are parts of local zeta functions in this family. Parts, I mean multiplicative parts. So the differential equation may not describe the full cohomology of the family. It may be some part of it, and therefore we'll only recover part of the zeta function. If we take sufficiently big differential equation corresponding to full DRAM cohomology, we will recover full local zeta function. So these things are very special. And I'm going to tell you today Dwork's uniqueness theorem, which says basically that when such a thing exists, it's unique. Here, there was this property that so remember, in general, when we have an equivalence between two differential systems, then solutions for equivalence have n² parameters. When we pick a fundamental matrix of solutions of a system, then this solution to the Frobenius equation will come with n² constants. They only depend on n² constants. So there is a particular choice. If there is a solution with entries in EP, there is only one matrix of constants up to scaling, which gives this solution. But for this uniqueness, we will need some assumptions on the differential system, which I'm going to name later. So it says that this is a very special object, and when we find it, we can compute a local zeta function in a family.